welcome you all to this new topic, that is non-uniform flow. Till now that we have discussed all about uniform flow condition and hydraulics of uniform flow, and today we shall be starting our discussion on non-uniform flow. Well, and under the non-uniform flow, of course, in our very basic introduction to the hydraulic engineering we were discussing, or to our introduction to the open channel flow, we are talking about non-uniform flow. There are different type of non-uniform flow, that is, say, gradually varied flow is one of that, where the flow depth varies gradually along the channel section, along the channel reach. And then there is another class that we call as rapidly varied flow, where the flow depth varies quickly, from a within a very small channel reach. And there can be another non-uniform flow that we term as spatially varied flow. Here say discharge is changing from section to section because of the fact that some side channel may contribute some discharge to the main channel. Again, some of the discharge from the main channel can go, a part of the discharge can go out from the main channel to a side channel. That way also there can be some changes in the discharge, or that way once the discharge changes, flow parameters are changing, velocity, depth, all can change along the channel reach. So that way we can have, due to different condition, we can have different type of non-uniform flow. And today we will be discussing on one of the non-uniform flow, which is called gradually varied flow. So our discussion will be on gradually varied flow, which is a type of non-uniform flow. Well, now to start with, let us just briefly give a definition of gradually varied flow. In our initial discussion also we did discuss that. Just to refresh it, let us say when say uniform flow is occurring, suppose uniform flow is occurring, then the force, the component of gravity force, that is when open channel flow we are talking about, it is the gravity force dominating flow. So the component of gravity force that is acting in the direction of flow and the force opposing that flow, that is the resistance force, are suppose in balance condition, and we are getting a uniform flow in the channel. Now, if somehow this balance is disturbed, and that this disturbance can be due to different reasons, if this balance is disturbed, then the flow, earlier it was moving with a uniform flow condition, means with a uniform flow, with a uniform velocity it was moving. Now, when this is disturbed, then the velocity will change, either it will accelerate or it will decelerate. And then when the velocity is changing along the channel, then its depth will also change. So that way we get gradually varied flow. So you can concentrate into the slide and we can define it like that. If the balance between component of gravity force in the direction of flow, always we are talking about the component of gravity force in the direction of flow, and the resistance force opposing the flow is disturbed, if this balance is disturbed, then the flow will either accelerate or decelerate, causing change in depth from section to section along the length of the channel, and this lead to formation of gradually varied flow. Well, so this is how we can define gradually varied flow, and this is how we define the gradually varied flow. Let us now see some of the practical cases or some of the practical situation where we can have this sort of gradually varied flow. And the one example, the first example we can take, this is the flow profile on upstream of a barrier, flow profile on upstream of a barrier. In a natural channel or even in a man-made canal also, in a irrigation canal also, many a time we give some barrier for utilizing the water for our better need, for our need. That means for better utilization of water, we can say. How, say in a river the water is flowing in this, suppose uniform flow is flowing, uniform flow is occurring like that. Well, now we want to carry the water from this river to some agricultural field for our irrigation. Then now when the water is at this level, it is within the bank and we may not be having any other device to carry the water from here to the irrigation field, to the agriculture field. Sometimes we may be doing pumping, sometimes we may use wheel to draw the water, but another way of doing is that if we put some barrier here, if we put some small barrier or maybe a large barrier also sometimes in case of dam and barriers like that, then what will happen, the water cannot flow through this level and it will be flowing like this, it will start flowing like this and then it is moving like this. Okay. On the downstream it is again flowing this way. So, that way what we have achieved, that we have raised the water level to this level. Now, our head is increasing, that is water is going to a higher level, and from this higher level we can carry, as our existing level is high, we can carry this water to a much far distance, maintaining the head. That means, say when water will be flowing from this level, we can carry the water, because when on the side, well, let me draw a section, cross section. Suppose this is the river, generally the slope will be in this direction and say our water is here. Now, if our water level is here, we cannot carry the water up to certain distance here, but if our water level we increase up to this much height, then we can carry by gravity, suppose making a channel, it can be carried up to this much of level where our level meet this point. So, we can carry it to a far distance. So, that way this is one way when we use some barrier and we raise the water level so that it can facilitate our irrigation in agricultural field. Now, this water surface that we are having here is not a uniform flow, because this depth is gradually increasing from section to section. Here depth is y, and suppose on the upstream it is normal depth, say here it is normal depth, on the upstream we can have normal depth, and then it is gradually increasing. Okay. Then it is gradually increasing like this. So, at this point it is normal depth, but after that it is gradually increasing and we are having different depth y1, y2, y3, y4 like that. And this flow is nothing but one example of gradually varied flow. Well, in canal also, for which is made for agricultural purpose, we sometimes increase the depth to carry it to the side channel or side feeder canal or field channel. So, that way also this water level is increased and we can get a gradually varied flow like that. Again, this gradually varied flow can be of different type, that we will be discussing later, but this is one kind of gradually varied flow. And this sort of curve is rising profile, it is rising, it is gradually rising. So, this is rising, and this has another name that we call as a backwater profile. Okay. Then another example is, name itself is backwater during tide, that we have experience in sea, that all the water that is coming in we refer as backwater, of course, but then during tide, what happened during tide, say it is a sea here. Okay. Let me draw the sea level. Suppose sea level is here and we are having uniform flow condition like that, uniform flow condition like that, and when during tide the water is rising up to this much level, then water from here will be rising like that, it will have to be continuous. So, it is rising like that, and then this is a gradually varied profile. we write it simply as GVF. So, this is a gradually varied profile. And one point we should remember, though in many a time we draw gradually varied profile, suppose giving a barrier, we are giving this barrier and we are drawing a line like this. Apparently, we get this feeling that okay, depth here is less, depth here is more. Then a question may come into our mind, that how the water is flowing from lower depth to higher depth, because here it is depth is higher and the charge is moving in this direction. But of course, total energy at the upstream level is always more than the total energy at downstream level, and that is why the water is flowing. And in reality, there will be some slope, like this barrier is there, and then suppose depth of flow is there, and it is rising like this, But if I draw a horizontal line here, then or energy line also if I draw, then you will be finding that energy at this level is higher than the energy at this level. So, though the depth is increasing, but if I draw from a particular datum here, then this is z, then this is y, then again due to velocity you will be getting v square by twice g, here it will be z2, say this is slope z1 y1, then v1 square by twice g, it is z2, then y2 plus v square by twice g, again v2 square by twice g, suppose this much, then we will be getting that energy line will be like that, energy slope. So, there will always have to be energy more here than energy here, and then only this flow is occurring, and in reality it is like that. And this change in depth is so gradual, that when we go to a field, this is not that much of visible. That means, on the upstream of a barrage or upstream of a weir, if we just observe the flow, we will never feel that water depth is rising, it is. So, this can be computationally checked, we can do the computation and we can check, and this is very important. Suppose for some reason we are making a barrier here, for whatever may be the reason we are making a barrier here, then water depth will be rising, and say bank level is here. Let me draw a fresh diagram. Say our bed is this one and bank level is this one, this is bank level, and then we are suppose when uniform flow is occurring with maximum discharge, then it is at this level. So, there is no question of over flooding. Of course, during flood time there may be flood, but generally the flood is not there, flooding is not occurring. Now, to raise this, to increase this depth, we are putting a barrier here. So, the water level from here will be rising like that, and it is flowing like that. Now, if we do not do the calculation beforehand, that is to what extent the water is rising, then what will happen, that if we give a barrier here, water will be coming here and it will be over flooding, it will be crossing the bank. So, it will create problem. I mean, our target will not be achieved, water will not be rising to that level, rather it will be flowing out from the bank. So, we will have to construct some marginal embankment, or on the side we will have to raise this bank. So, this is the bank level. So, that we will have to also rise like this. This is the bank level we will rise. So, to what extent? Now, we cannot rise this bank. Suppose we know at this point our bank height will have to be this much, but that we cannot carry, or we need not carry the same height, same raising up to this point, because water is rising from this point. So, we know that up to this point, from this point water level is crossing the bank. So, we can increase our bank height like this, and that way we can save our expenditure in raising the bank, and we can achieve economy in such projects. So, for those purpose also we need to know how the gradually varied profile will form, to what extent it will go, and this sort of calculation will be coming, that we will be discussing in computation of gradually varied flow. Well, this is just we are putting some example where gradually varied flow can occur. Then let me take another example, that is confluence of two rivers. That is also another case where gradually varied flow can occur. Confluence of two rivers, say one river is coming like this, mainstream, and another river is, another tributary is joining this way and it is flowing like that. Well, this is coming some discharge here. Now, at this confluence, sometimes what happen, say this river has this catchment on the upstream of this particular section, and this river is having this catchment. Catchment means whatever rainfall is occurring, that is coming to this particular point, whatever rainfall is occurring, it is coming to this particular point, to this particular river. So, if suppose heavy rainfall is occurring on upstream of this river, then the depth or discharge in this stream, in the main stream, can increase significantly, and then depth of this stream can increase. Now, earlier suppose if I draw it like this, this is the main stream and this is the river, side river, this river is this one, it is carrying Q1 and this river is carrying a discharge of Q here, it is flowing like that. Now, earlier suppose it was in this form, okay, earlier it was like this. Now, when this level will be increasing, suppose due to increased rainfall in the upper catchment, this level is increasing, then on this channel the water level will be rising like this, and this is not a uniform flow. From section to section, this depth is increasing. So, at confluence of two river, this is the confluence, at confluence of two river and to upstream of the tributary, there can be gradually varied flow profile. There can be gradually varied flow profile, and knowing this is important for various activity, because when the water level rises, that means, well, we understand that energy level, energy difference is there, but energy difference will definitely reduce from that of the original condition. So, the flow velocity in this part will be less, in the tributary will be less, and this can happen, suppose it is a river and it is a drain, then also this situation can happen, and then flow velocity here will be less, means less amount of water will be released, or this channel will be carrying less amount of water. So, then it was carrying earlier because of the reduction in the energy level, and that sometimes can lead to flood congestion in the upstream area here also in this channel. And so, these things are important in various analysis. We use the concept of gradually varied flow in this sort of channel confluence. Then there can be another situation on upstream of a canal drop. Okay. Many a time we have some canal, we have some canal like this, and there can be, suppose in a very steep slope, okay, suppose in a very steep slope, let me use in a very steep slope, we can have this sort of situation, say natural channel is very steep, and we want to make a canal in this direction, then it may become difficult due to many reasons for constructing a channel, a canal of this slope. So, what we do, because a very if we construct a very steeper channel, then it may cause then flow velocity will be very high, and then with high flow velocity there may be erosion or there may be damage to the channel. So, what we do, that suppose we construct it like that, then we cut some portion here, we make a canal drop, and then we remove this portion, and then we make another channel portion like that. This part can be deposited here, and then again there may be a canal drop like that, and that way we are negotiating the slope. So, ultimately the canal will be carrying water like this, and then there is a fall, then this is going like that, then there is a fall, then it is going like. So, water is flowing like this, though our original slope was that one. So, in this sort of canal drop, if I just draw one canal drop like this. Then what will happen? Water will be flowing. Suppose this is uniform flow depth for a particular discharge Q for this bed slope. For this particular slope, we have this much of uniform flow. Then when water is falling, it will be coming like this, and then it will be falling like this, and then there may be some other phenomenon here. We are not discussing that part right now, but we are talking about what is happening on upstream of this one. So, this water surface is gradually coming down and the flow depth is changing from section to section. Here it is normal depth yn, then it is y1, y2, y3. Here the depth is gradually decreasing. Here the depth is gradually decreasing because of the change in the flow. Okay. Now, this sort of flow is also gradually varied flow, and that flow we call as drawdown curve. We call as drawdown curve. So, basically it is a drawdown profile. Earlier we have seen some of the cases where the channel depth was flow depth was rising, but here the flow depth is falling, or we can call falling profile. This is a falling profile. So, there may be two class, one is rising profile, another is falling profile, and in the falling profile we name this as drawdown curve, rising profile we name as backwater curve. Okay. Then let us see some other example due to change in bed slope. Okay. This is somewhat similar to that one where we are talking about canal drop, but here say actually canal drop is not there, but there can be some change in the bed slope. Say bed slope is changing this way. Well, now from our understanding of uniform flow, we have seen till now that suppose a discharge Q is coming here, then for this slope, suppose our uniform flow level is this much, NDL 1, suppose in this section 1, section 2, section 3. Now, here as the slope is increasing in the channel 2, as the slope is increasing, so obviously the depth of flow or the uniform depth of flow will be lesser than that of the uniform depth of flow for section 1, for the channel reach 1, because discharge remaining same, slope is increasing here in the 2 then 1. So, uniform flow will be coming lower. So, this is suppose my NDL, this is NDL in this level, normal depth line 2. In the third section again, as the depth of flow, as the slope is flatter, then even the first one depth of flow, normal depth of flow will be again increasing, NDL. But these are all about the normal depth line we are writing. The flow profile, that is surface of water, will not be moving like this and then suppose straight moving this way, then dropping here, again moving like that, then rising here. It will not be moving like that. But in a channel, when we allow the water to flow freely, it will always try to attain the normal depth condition. Of course, if we make some disturbance there, then it will be disturbed, and if we allow it to flow continuously for a long time without any obstruction, without any drop, then it will try to attain the normal flow condition. So, what will happen here, if we assume the flow is coming like this at this normal depth, but here it will try to meet this normal depth, and so it will gradually come down, and then it will be coming like this, and then of course, further detail is necessary, that is whether this flow is becoming supercritical or whether all these flow are remaining subcritical. Those issues are there, and right now we are just simply considering that this is changing like this, and then from here it will be again moving on to this particular side. Okay. Let me just talk about this part, because further detail will be, to know further detail will be requiring some knowledge of this supercritical subcritical combination, and that we will be discussing later. But when the change in channel slope is there, this flow depth are changing. Here also the depth is here uniform flow depth, and then it is changing gradually in this part y1, y2, y3, and here it is uniform flow, say yn. If this length is sufficient to form the uniform flow depth, then ultimately it will come to uniform flow depth, and then in this part it is rising, in this part it is rising. Say we can write y1, y2, y3, y4 like that. For the second section, here it is normal depth, then it is coming down like that. But all these part are gradually varied flow, and when we talk about different type of gradually varied flow, then this part will be one GVF, this part will be another gradually varied flow. This is a drawdown curve, this is also a drawdown curve, but it is the name of this gradually varied flow profile and name of this gradually varied flow profile, two gradually varied flow profile may be different. But right now just we need to know that gradually varied flow profile can form on the earth surface in a channel due to change in slope. Okay. This is one example. Then another example is, say, on downstream of the sluice gate, on downstream of a sluice gate. So, what is sluice gate? Many a time we provide sluice gate to control or to regulate our flow. Say water depth normally is flowing in this level, let me use a dotted line. Normally suppose it flows, uniform flow occur at this level. Now, somehow for some reason we want to stop this water, so that we are using a sluice gate here, and of course, when we are using a sluice gate, and then we will be releasing the water also when required. So, when we block this one, water level here will be rising like that, and then when if we close it completely, then of course water from this side, suppose in some situation where say there is a downstream channel and on this side, and what this is a tributary, this is a main river, and from the main river suppose the at high flood period water enters into the tributary, we want to avoid that. So, we are putting a sluice gate here, so that when the main channel water rises, then we are closing this and the water cannot come into the chap channel. So, this is one example where we are using sluice gate, and there can be different example, and just one example I am stating. And then when this water level will come down after flood time, when this main channel river water is come down, then we again release the water, which again, because in this channel, in the small channel also water was flowing, and there will be some deposition of water due to rainwater and all in this side. So, that water we need to release once the water level come down here. So, suppose we are releasing the water. So, then we are just opening this gate, and then we are allowing the water to flow. So, this water will be flowing, and in this channel, as we know that its normal depth is this line, NDL is this line. So, this water will try to reach the normal depth line from this level, and of course, as I have explained, or as I have stated, rather have not explained, as I have stated that the flow condition here will depend, here means in this portion will depend on the condition whether it is supercritical and that part is subcritical, or whether both the part is supercritical, or whether both this part is subcritical. What is the combination? Depending on that, sometimes we can have hydraulic jump in this portion, and sometimes we can have gradually varied flow profile, and sometimes we can have a gradually varied flow profile rising and then a hydraulic jump is occurring. So, different conditions may be there, but one point is that on the downstream of this sluice gate we can always have a gradually varied flow profile. It may be followed by a hydraulic jump, or sometimes there may not be hydraulic jump, or sometimes instantaneously just after releasing from here without any gradually varied flow profile also we can have a hydraulic jump like this. In that case, we will not be getting gradually varied flow profile. So, those details will be coming later, but this is one condition where we can have gradually varied flow profile. Okay. Well, that way we have discussed some of the practical situation where we can have gradually varied flow profile in our day to day life, in our day to day engineering activities. And then we can move on to the theory of gradually varied flow. Well, and when we talk about theory of gradually varied flow, then we must take the name of Ballinger, who first developed the theory in 1828. In 1828, the theory of gradually varied flow was first given by Ballinger, and of course, it was for a simple situation and lot of assumptions were made, and then still this equation is very much useful. Well, now whenever we talk about some theory, then to develop that theory, that means to develop a mathematical expression for a practical problem or a practical situation like gradually varied flow. Say one problem and we want to derive one equation for that, we always need to make lot of assumption, because if we try to develop one equation for representing a particular flow phenomenon considering all the practical situation, then it becomes so complex that it may not be possible, or we may not have complete understanding of all the processes involved in that. And why we make those assumptions? With all those assumptions also, after simplifying the problem also, even whatever answers we get, that has lot of practical importance. That is, with this understanding itself, we can do lot of engineering work, and as such we are always considering some assumption, and then we are developing those theory, but we should be very much aware of those assumptions, because once an equation is given, normally students do use it, and when in practical field they apply it, and sometimes they find that what the calculations they are doing is not matching with the practical situation. Then they must know that, okay, what are the assumptions that were there in that derivation of the equation, and then only they will be understanding that, okay, this sort of differences may be there. And when we know the assumption, then we know the limitation of that particular governing equation, and then we will be able to use it more judiciously, more wisely for our practical application. Well, that is why I am just giving some of the important assumptions that are suppose very obvious, and of course, apart from these assumptions, some smaller assumptions are always there which we are not mentioning here. First assumption that you can concentrate into the slide, that is the head loss is same as that of the uniform flow. Well, head loss is same as that of the uniform flow. That is, the uniform flow formula like Manning's or Chase's formula are applicable. Already we have discussed that Manning's formula, Chase's formula, all these are uniform flow formula. Now, these uniform flow formula basically deals with the friction loss, that is indirectly coming as head loss. So, these head losses are same as uniform flow, because in gradually varied flow the depth is changing and there will be difference in the head loss basically, but we are considering that this head loss is similar to that of the uniform flow, and that is why for some of the calculations we will be still using Manning's formula and Chase's formula in the computation of gradually varied flow. Well, this is one of the assumption. Then second assumption is that the channel is prismatic. In that derivation we are considering that channel is prismatic. Now, what we mean by prismatic channel, that perhaps we remember, because we have discussed this already, that when channel section does not change in the doesn't change in the entire channel reach or along the channel, then if the channel slope is also not changing. So when channel cross section and slope do not change along the section along the channel reach, then we call this as a prismatic channel. So in the derivation of gradually varied flow formula governing equation, in the for getting the final form, it was assumed that the channel is prismatic. But in real situation, channel will not be prismatic, because a channel can be always like this, channel can be always like this. Now say a formula is given and we want to know, this is the plan view I am drawing, this is a top view of the channel, where the channel width here is this much, here is this much, here it is this much, again it is increasing to that much. Well, now if we use that formula directly, and we are suppose computing gradually varied flow in this channel, depth here and depth here we want to know, depth here and depth here. But if we do not remember that there is an assumption that channel is prismatic, then we will be ending up doing wrong calculation, because if we just try to use that formula and if we compute the flow depth between this and that, it will not be correct, because in this portion the channel is not prismatic, here it is changing. So what we can do for our practical purpose, we can consider that from here to here a small reach we can take, and from here to here where it is even we can make it smaller, and we can consider that from here to here this channel is prismatic, because it is a very small distance and change in the cross section is not that much significant. We can take average section width. Then from up to this much, suppose we are taking like this, then from here to here we can see the channel is more or less of uniform size, and if slope is also not changing, this portion we can consider as prismatic. From here to here we can again consider as prismatic, from here to here we can consider prismatic. Then again in this expanding portion we can make some smaller section and we can consider that channel is prismatic within this section. So when we will be using the formula, the governing equation of gradually varied flow between this section and that section, say between this section and this section, then it will be giving more or less correct result. We will be using governing equation between this section and that section again. So this will be giving us correct result, and we can use this section and that section directly. Then we can apply this to the same equation between this section and that section, because more or less this part is prismatic. So that understanding is very important, what assumption we have. This is what the channel is prismatic. Then another assumption is that energy coefficient is 1. We were talking about alpha value, energy coefficient, I mean the velocity coefficient. Within velocity coefficient we have energy coefficient and momentum coefficient. This energy coefficient alpha is 1, that is the variation of velocity within the section, within the cross section is, suppose we are computing gradually varied flow, the velocity may be different here, but we are assuming that this is uniform. So in the actual field, if this difference is quite significant, our computed result may be varying from the actual result, that we need to know. And we need to know that if this variation is small, then well we are applying with more confidence our equation, and if it is quite high, then of course we need to consider the value of alpha. In the final form we may not be having that alpha, but if this variation is very high, we need to consider this alpha value. Then another important assumption, that this assumption roughness coefficient n, that is a Manning's roughness coefficient n, or it may be Chase's roughness coefficient as well, is independent of depth. Now when we were discussing our uniform flow formula, then we very specifically pointed out that Manning's roughness coefficient varies with the depth. If our depth increases, then our roughness value changes. But for computing the gradually varied flow between two sections, if we apply that equation, we will be considering a single n value or single roughness parameter, means that we are violating that very basic condition of Manning's roughness, that is it changes with depth. But however, we are assuming that change in the roughness parameter is not that significant for the variation that is occurring within the gradually varied flow portion, and that is why we are considering that n value is not changing. And then of course, if we are aware about that, then what n value we will have to use, that is the n value for a very smaller depth if we use, then it may not be applicable for a very higher depth. And similarly, if we use the n value for a very higher depth, that may not be representing very correctly for a very smaller depth, then we can use the n value intermediate between these two. And so, knowing these assumptions, we should work, that assumption is there. Then another assumption, that bed slope is very small, bed slope is very small. Generally in natural channel, when we find this gradually varied flow, in most of the cases, of course some exceptional case will be there, but in most of the cases when we find this gradually varied flow problem, as we have already discussed some of the cases, the bed slope is generally not that high, and we can consider this to be very small. And when we consider bed slope to be very small, means theta is small, and some other considerations are automatically coming, like if we remember talking about the pressure, water pressure, hydrostatic pressure, then or the pressure of the flowing fluid, in steep slope the pressure is different, but in flat slope the pressure theta, if we neglect, this expression is different. So, that is the hydrostatic pressure condition we get. So, this ultimately lead to hydrostatic pressure prevails, this lead to the condition that hydrostatic pressure prevails, and the pressure correction is not coming into picture. But in a flow situation where slope is very high, or even suppose in a gradually varied flow, in this portion, suppose this slope is very small, but the surface slope is very steep, this portion. Here also, in fact, the flow is moving as a curved flow, as we discussed in our earlier classes, and there hydrostatic pressure may not be exactly valid. So, we may need to apply correction here, and similarly when the slope is very steep, we may have to apply correction for pressure, and if we do not apply, at least we should know that some amount of error we are introducing there. So, this assumption is also important, and then we will be deriving this equation for flow depth, considering the flow as one dimensional and depth averaged. Depth averaged means the velocity that we are talking about is the velocity considering the average depth, average velocity for the entire depth, because we know the depth velocity here will be more, here will be less, and there may be a velocity profile like this. Of course, highest velocity may not be at the surface, it will be generally highest velocity will be little lower than this, that we have already discussed, but that velocity variation we are not considering in this particular derivation, and then we are having that for the entire depth we are considering a single velocity v, which we refer as depth averaged velocity. So, velocity averaged over the depth, and of course, this equation is one dimensional, we are not considering two dimensional, but we can have two dimensional expression also. Well, with these assumptions being on the background and understanding this assumption, now we can move to derivation of the governing equation. Well, so let me draw a channel like this, and let us see that this flow is moving like that, and let me write the expression for a section here, and of course, we can have a section here and then this is the datum. Of course, this is say uniform changing like that. Then let us see what will be the energy, total energy H total energy H in a section 1. As we have already written that part, say this is Z1, this is say y cos theta. If this slope is theta, in reality it is y cos theta, means depth if I draw like this, and then it is alpha v square by twice c. That part we have already discussed in one of our classes. So, I am not going to discuss this again, but this is alpha v square by twice c. So, total head we can write as Z1 plus y cos theta plus alpha v square by twice g. Okay. This is the total head. This is the total head at any section. Well, to derive that equation, what we can do, we want to see that how this head is changing with respect to the flow direction. If flow direction we put here as x, then we can write what is dh dx, that is how this dx h is changing with respect to x. So, we can write it as say dh dx, that is taking derivatives with respect to x. This is equal to what we will be getting dz dx. I am not using the term 1 because it is I am writing in general for a particular section. Then plus we can write say d dx of y cos theta plus say d dx of alpha v square by twice g. Now, in this expression, this dh by dx term, that is the head. Now, if I draw here z2 y2 cos theta, this is y1 cos theta, and alpha say v2 square by twice g, then here I am getting a total energy level H2, and then if I join this, then I am getting a line which we call as a friction slope SF, and this theta in fact we write as bed slope SB. Okay. Now, this line should be horizontal, of course. This is bed slope SB, and this is the slope of the friction line SF. So, rate of change of head with respect to x, that is nothing but slope of this particular line, because we are drawing this joining the total head at two different points. And one point again here we need to mention that if our section we are considering 2 and head here we are joining, we are getting a slope. If I take another section in between, total head will be different, and SF between this point to that point and from again this point to that point, both may not be same. So, here we are taking basically average friction slope, because friction slope at this point and friction slope at this point may be different, but it is varying. As our section will be smaller, as these sections will be smaller, we can consider this as average friction slope. And as head is falling in this direction, head is falling because energy here is more, so head is falling in this direction. So, we are writing this as minus SF, minus SF. Well, if we want to give the value of SF somehow, then the numerical value of SF we need to give positive, because in the equation we are using the negative sign to indicate that it is falling. So, in the equation itself we are using this sign concept, and so numerical value when we calculate for SF, this we should calculate positive, this is SF, because already we are assigning the sign to that particular considering the direction. Similarly, this dz dx, again z1 is dropping to z2, so it is also falling, we are considering that it is falling from this direction to that direction. Of course, there may be just adverse slope also, but here we are considering that it is falling from upstream to downstream. So, this dz dx is nothing but the bed slope, and this also we are assigning a negative sign. So, numerical value of SB when we are considering positive when it is falling, because we are already putting a sign. So, numerical value we need to put positive for a falling one, sign is already there. And if it is adverse slope, suppose the bed is rising like that, then numerical value itself we will have to put negative, then only with this minus sign it will be coming as positive, that is the rising one. So, these things we should be careful. Well, in the derivation what we are doing, that if we know, then we will be putting the sign correctly. And then we can write this as cos theta, this has nothing to do with x. If we consider the slope is not changing in this portion, then cos theta we can just bring here and we can write dy dx plus this particular expression we can write in a form that because this v square velocity is changing from section to section. Here it is v1, here it will be v2, velocity is changing from section to section. But this velocity change we can directly get in terms of y, because depth is changing means we can get it the discharge remaining same, q we are talking about the same q. So, we can have with the change of depth this velocity is changing. So, we can get it in the form that we can write it as plus, say let us write this change in velocity in terms of y we can calculate, because x of course in the direction of x it is changing, but how it is changing with x, that is not known to us right at this moment. So, let us see how it is changing with y, then we can take it again, multiply it how y is changing with x. So, that will ultimately give us the d dx of this part. So, what we will write d dy of alpha v square by twice z into say dy dx, because we have differentiated with respect to y. So, let us differentiate y with respect to x. Again original differentiation, our target is with respect to x. So, we are writing this. Now, this equation we can have in this form that SB minus SF, SB I am bringing on this side, this equal to say cos theta into dy dx, cos theta into dy dx plus say d dy of alpha v square by twice z into dy dx. And this we can further simplify now putting all those assumptions. Well, this let me write as dy dx, because our target is to write one expression for gradually varied flow profile. Well, gradually varied flow profile means if we can get how y is changing, how these depth are changing with respect to x, how these depth are changing with respect to x, that is dy dx, how these are changing, and then if we can get these in terms of some known quantity on the right hand side, then definitely we are getting our answer, we are getting an equation, and from that equation if we solve it, then we will be getting, we can integrate it, we can solve it by different way. If we solve it, we are definitely getting depth at different section. Once dy dx is known, as a function of some known parameter, if we solve it, we will be getting y at different x, and that is what our target. If we know that, then we will be able to solve what type of profile it will be, how the profile is changing. So, let me write it in this form, dy dx into cos theta plus d dy of alpha v square by twice g. Okay. Well, from this dy dx will be, we can write the dy dx is equal to SB minus SF divided by cos theta plus d dy of alpha v square by twice c. Okay. Now we can just introduce some of the assumptions that we had just before starting derivation of this equation. So, those assumptions are the first, that theta is very small. For small value of theta, we can have cos theta is equal to 1. Then again, for alpha equal to 1, that is, we are considering say variation, neglecting variation of velocity within the channel section. So, neglecting variation of velocity within the channel section, what we can have within the channel section, if we neglect this part, then our alpha is equal to 1. So, our equation reduced to say dy dx is equal to SB minus SF divided by 1 plus d dy of v square by twice g, d dy of v square by twice g. Now, we can further simplify this expression. Let us see how we can write d dy of v square by twice g. So, v square, again this v is nothing but depth average velocity. So, as we know the q, this v can be written as d dy of say q square twice g by a square. Now, v is varying with depth, but q is not varying, v is varying with x and y, but q is not varying with y. So, q is constant. So, for this derivation is concerned, so we can write this as d dy of, we can write q square by twice g, these are constants. So, d dy of 1 by a square. Now, this part if we just do the derivation, we can write q square by twice z. First a square, a is definitely varying with y, but of course, we can derive it with respect to a, then we can write dA dy. Let us do that. So, it will be a to the power minus 2. So, it is minus 2 into a to the power minus 3, that derivation, and then we can write dA dy. And as we know in a section that if this is the area, for a small increase in y, if the change in area is dA, then if top width is t, we can write dA, actually dy into top width t is nothing but dA. So, dA by dy is nothing but t. So, putting this as t, what we can write this expression, all these are coming as q square, this t will be t, 2 and 2 is getting cancelled, minus sign is remaining here, q square t by g a q. So, putting this expression for d dy of v square by twice g, we can write say dy dx is equal to SB minus SF divided by 1 minus q square t by g a q, and this is what is called as governing equation of gradually varied flow. This equation number I am just putting as A. It is very important expression, and this equation is used for various practical purpose. And of course, this q square t by g a cube, as we did earlier also, we have done several times, this can be expressed in terms of Froude number also, and that is why we can write say dy dx, we can write it in the form the dy dx is equal to SB minus SF divided by 1 minus, it is q square by a square will become say v square. So, we can write it a v square, and a by t, that will become d. So, it is GD, and that can be written as SB minus SF divided by 1 minus FR square. So, that is also another form of governing equation, that dy dx is equal to SB minus SF divided by 1 minus FR square. So, this is also one popular expression I am writing as B. So, that way this particular governing equation we can have in different form, and this is this expression for a rectangular channel or for a wide rectangular channel, we can again express it in a different form in terms of normal depth and critical depth. So, that will be coming, and that we will be discussing. Many a time we write this expression as dy dx is equal to, suppose SB we are bringing here, and then we write 1 minus SF by SB divided by 1 minus, okay, let me write it as q square t by GA cube, and then we can have this SF by SB in terms of as a function of YC and YN, and this also we can have in terms of YC and YN, this we can have in terms of YN, and this we can have in terms of Y and YC. Like that we can for rectangular channel, these are for rectangular channel we can have it, for wide rectangular channel we can have it. So, for different channel we can simplify this particular equation into different form, and then we can from that we can derive lot of our important understanding, or we can see how the flow can be classified, how the gradually varied flow can be computed and can be classified. Well, one important point just I want to mention before going to all these, that is this equation dy dx is equal to SB minus SF divided by 1 minus q square t by GA cube is a non-linear differential equation, because this SF is also a function of y, and from this expression you cannot separate out your y value, that is we cannot solve it directly by integration. The solution of this equation by direct integration is, of course with some assumption it is possible, but we cannot solve it directly, and that is why for solution of this equation we generally take recourse to numerical method, and some other approximate solutions are there. So, all those different methods existing for solution of gradually varied flow equation, computation of gradually varied flow, that we will be discussing in the next class. And as we have already mentioned, there are different classes or classification of gradually varied flow are also there. So, when the flow is occurring on a mild slope and we are getting a gradually varied flow, then we name it in a different way. When the gradually varied flow is occurring on a steep slope, then we name it in a different way. And sometimes it may happen when we are talking about uniform flow, then we found that when it is a uniform flow occurring, if it is on a steep slope, then this uniform flow depth yn is always less than the CDL line, NDL is always less than the CDL line. But in gradually varied flow we are putting some obstruction here, though the slope is steep slope, water may be rising like that, and so it is going to this level, that is the depth of flow at any point may be more than our critical depth, though the slope is steep. So, based on all those conditions, that is if a flow is occurring above critical depth in a steep slope, the name will be different. So, in a very systematic way we classify the gradually varied flow considering all these different concept, and then we name them, and then after that we will be going for computation of gradually varied flow. So, in the next class we will be doing all those. For today, this much is sufficient. Thank you very much.